And this is basically 50% graphene and 50% aluminium. Expectations are we'll be able to have a rack of these all sit next to each other, no cooling required, no air required, completely, you're talking 95% cell to pack density. But we're still talking very, very fast charging. We're talking 70 times faster than what the lithium batteries are charged at.
Well, today I'm joined by the founder and CEO of Australian-based the Graphene Manufacturing Group, Craig Nicol. Thank you so much for taking time to talk with me today, Craig.
Thanks, John. Love to be on.
Definitely. Well, the Graphene Manufacturing Group, I love the name. It tells you what the company does. They manufacture graphene, but that's not just it. They take that graphene and they make various products, including HVAC coatings that really help with the efficiency of HVAC systems. Of course, that's really important for sustainability, etc. They also make additives for oils that go in machines and I imagine cars and other heavy machinery. But what I want to talk about, and I think what the video is going to be mainly about today is the aluminum ion battery that uses graphene. So Craig, could you just talk a little bit, first of all, kind of introduce that graphene aluminum ion battery and kind of talk about in this intro here, in a world where we hear about the lithium ion battery that has usually a nickel cathode, sometimes an iron cathode, what makes the aluminum ion battery so different to that battery?
Yeah, thanks, John. I mean, it's great to be on your channel. There's a lot to talk about with battery chemistries, and there's quite a few new ones coming out, and people should be aware of them. It's not just lithium-ion batteries out there. Aluminium ion has been around for a while. University of Queensland, who developed our technology that we are now exclusive licensor for globally, just made it better. Stanford did some work in 2018, 2019, and did some really good work. Musk tweeted that when they came out with their energy density, you great work, guys, but you need to do better. Well, we've done 4 times better than where Stanford got to. And Stanford had done a really good job at that point. So some really core piece of information. First of all, lithium-ion batteries use the lithium atom, and they lose 1 electron when they come across to give that charge capacity. Aluminium ion has 3 electrons. So that means for every atom that goes across, you have the potential of 3 times the charge. So that automatically means that you have 3 times the potential for this battery over and above what a lithium-ion battery is for energy density, which is massive. So that's one thing. The next thing is, of course, it's made from aluminium, which is 1,000 times more abundant and a whole lot less costly than lithium, and it doesn't catch fire when it's reacting with water, which is what lithium does, which is why you have lithium fires out of batteries and why you have lithium batteries, when they're swallowed by kids, can kill them because they leak through the seal of the battery, and then they can then touch the water and burn the esophagus out. So, lithium was chosen because it was one of the lightest materials available, lightest metals available, and also it has a very good voltage. It has up to 4 volts when you pull an electron off it, which is pretty amazing. Aluminium, we're currently sitting at about 1.7 volts when we pull an electron off it, but you could get up to and there's a potential to go up to 4 volts as well, and that's what we're also working on. But as your listeners would no doubt, your viewers would no doubt know, if you have a voltage of 1.8, you just double the 2 batteries, and then you've got a voltage of 3.6 volts. So you're back to where lithium is. So, and most of the world's batteries that gets used, which is the AA batteries or what's called primary batteries, well, they're actually already 1.5 volts. So we're already in a very acceptable range of voltage. We're already pretty good energy capacity. We're sitting calculated energy density of about 150 watt hours per kilogram. Now, right now, we've got access to effectively 1 of these electrons. But as we work on more electrons out of the 3, you can see where our voltage will go. You can also see where our energy density will go. And we expect, therefore, to have much higher energy density as we do that work. But the other thing an aluminium ion battery holds, which is really quite an amazing part of it, it's commonly called a hybrid supercapacitive battery. And that's really quite rare. So these are very low resistance batteries. So very low internal resistance. So that means pretty much every amount of power you put in goes into the capacity as much as you can get. There's a few obviously other constraints. And what you also see is an ability to handle very high power charging. So very high current charging. So what that lends it to is a very high power density. Now power density is not talked about for lithium-ion batteries because it's not that good. You don't hear about power density, which is how fast you can accelerate, right? Energy density is how long the car can go, but power density is really how fast you can accelerate. You don't talk about it because it sits at around 200 or so watt-hours per kilogram, around there. And typically, where you charge or discharge a lithium-ion battery beyond that, it starts to have problems. So there's an awful lot of battery management systems in place to be able to manage the current around the lithium-ion battery. And we don't believe we'll need that because ours has the ability to take a very high current. We're talking in testing anywhere up to 70 times faster in discharge and charging. And then still have a very good energy density after that. So that's another opportunity that our battery has. So what this opportunity would mean then is you would have this battery, which is no longer the limiting factor in charging. It'd then be how fast is your phone charge cable actually able to charge your phone? It would then be how fast can the infrastructure charge your car? And that's then, up to that infrastructure piece, which obviously there would be constraints there. So that's another huge benefit of this, or difference that the aluminium ion battery has as well.
Very interesting. We'll talk about charging in a minute. I definitely want to go there. Also, energy density. I'm going to do some comparison there and talk about an actual battery pack level energy density, not just a cell level. But obviously, one of the big keys to this battery is you use graphene in the battery. Where I think from what I read, it's graphene cathode. So can you talk a little bit about graphene in the battery, a little bit about how it's used, and then also why it's so important for that particular battery tech?
Sure. So this is one of our new pouch cells, and this is basically 50% graphene and 50% aluminium. So how can you have that, and why is it important? So the aluminium, as we've described, is used as the ion. It's also used as the anode. Now, the cathode, which is the opposite of how you often see lithium-ion batteries, the cathode has the graphene or the carbon. And why we're using graphene and why graphene is enabling this is that we're able to, through a process with University of Queensland, we're able to split the layers of our carbon atoms apart. First of all, we make the graphene a certain way, and we're doing a lot of work to make sure that we make that graphene the same way every time, and we make that from natural gas. So it's a very, very clean process. We end up with hydrogen as the main byproduct. So we make this graphene that's enabling the interlayer spatial atom distance to be able to receive the aluminium ions. And that's really important because the more aluminium ions you can store in the carbon per kilogram of carbon, the more you have energy density, the higher the energy density is. So I think that's the key thing. And how that was done is UQ developed a way to split the carbon and make holes in the carbon. And that's really the fundamental difference between where Stanford got to and where University of Queensland got to in our battery, is that they were able to put more atoms inside the holes, the aluminium atoms inside the holes of the graphene. And so that comes from two things. One is making really good graphene without any type of contaminants. So no oxygen, no silicon, just carbon, just pure carbon atoms, which is what we do every day for years. And then it's being able to put them in and insert them in a way which enables them to come in and out. Now, you always lose some. You always lose some. That's just in lithium batteries, that's what you lose as well. It's called round trip efficiency. You lose, something 20% or so, or 15%. So you get about 85% or so back. That's what we get as well. We get around that round trip efficiency. And then what you're looking at is then, well, what is the failure mechanism for that battery? Now, lithium-ion batteries have a failure mechanism which is why we all tend to update our phone after 3 or 4 years, because the lithium it gets lodged into the receiving electrode, and then it builds that into a point where it can't get them out anymore, and creates this lessening effect of charge capacity. We don't have that. So we don't have that building up of ions in our graphene. And so it can continue to operate in such a form for thousands of cycles. So that's the other benefit, is that we're still working on what is the main failure mechanism. And in fact, there have been other studies done with similar type of products, similar type of batteries, and they've gone on for 250,000 cycles. As in, they're so stable because they almost act like a supercapacitor, that it could actually go on for much longer than we're currently expecting, around 3,000 cycles. And your lithium-ion battery is really only 600 to 1,000 before it starts to be problematic. So that's another reason why this type of battery enables the next generation step change, and why we're getting a lot of big companies asking us to how we can collaborate with them.
I want to talk too, as we move through this conversation. So traditionally, obviously you make your own graphene, so this is maybe kind of a moot point, but traditionally graphene is very, very expensive. Like, you look at the cost of graphene, and that's one of the reasons why graphene isn't used in a lot of batteries. It's not because it's not great, it's because it's really expensive. So can you talk about how you are able to do it such a way that it's cost effective? And then talk a little bit about, like, obviously now it's more expensive per battery, but in the future, when your product is more mass produced, what is the price per kilowatt hour, or however you want to measure it, as compared to maybe, say, a standard $100 a kilowatt hour lithium-ion battery, kind of an industry best? How does your price compare as it's launched in the future?
So first of all, our costs will be definitely very competitive, if not far below where lithium-ion is at scale. We're obviously not at scale. We still make our batteries by hand. And because once you get the chemistry right, that's when you go into the automatic process, which we're hopefully going to do shortly, into little coin cells. So there's, I guess the costs come down to two factors. One is how much it costs to our graphene, and how much does it cost to put this together because the aluminium is obviously a pretty low cost material. The cost of our graphene is really quite easy to understand. Around the world, you buy natural gas, which is what we use. We don't do any pre-processing. Natural gas comes in gigajoules or MMBTUs. It depends on which part of the world you talk a different language, but they're actually all about the same. And you get about 20 kilograms of gas for that price. And in America, you could possibly buy that for $10, maybe $5, depends on where you are. You might have to pay $20. Let's just say it's $20, which is a very expensive price in America, but let's just say it's $20. That means you're getting 20 kilograms of gas for $20, and 15 kilograms of those atoms are actually carbon atoms. So that means for $20, you're getting $15 kilograms of carbon atoms delivered to wherever you want in a beautiful pipeline. So it's a very competitive cost. So you're talking, somewhere around $1 or so. Now, we obviously don't get all those carbon atoms. Depends on what we want to do with the graphene, because we make different graphene shapes. continuously, depending on what we want to put it into. They're all different shapes, and that's part of the IP to get to where we are. And we've been doing that for near 6 years. But that's the first thing. So the cost of the graphene is, it's all in how we did it, not necessarily the actual cost of the good. And we've spent a lot of time making it a very low cost, competitive product. We actually built our graphene plant and process around supplying graphene for concrete. And we got there, we could make it economically, and then we realized people don't really want stronger concrete. It's kind of strong enough, you know. It could help, but it doesn't really set people alight. So that's why we shifted to the energy space, which is obviously ex-shell. That's a lot easier to market to as well. Now, the other part of it is, how do we make the battery? And this is the really quite special thing. There's a lot of new batteries coming out, like solid state, silicon anode, and they've had to go and reinvent the way batteries are made. Lithium-ion batteries have been scaled successfully. It's a complete success case. In fact, it's too successful. Everyone's trying to put it in things that it really probably shouldn't be put into, you know, with the overheating potential and the fires, but it's a complete success. And it is fundamentally the reason why we're having an energy transition right now, is because we have that. So we need to nurture it, need to keep pushing it along to keep this energy transition happening. But there's about 12 machines that you need to make a lithium-ion battery, and they're well identified. There's about 40 companies in the world that make them, and you can buy them individually. You can put them together. You can put robots around them, and it's well documented. And you know, Bosch is our partner in this space, and they make their own pouch cell manufacturing equipment, and they'll, you know, what we work with them on is to actually bring it all together. Now, what's interesting is you take those 12 lithium-ion battery cells to make the batteries, and we use about 9 of them. So that's how easy our battery is to make, is that we actually have less stations of existing equipment, and even those equipment's even less difficult to make. So, you know, I think at scale, our cost and our ability to produce this, also with a recyclability angle, the carbon, you know, it's got 5,000 years half-life, right? You lose as an isotope every 5,000 years. That's how you carbon date something. It's not going anywhere, all right? We form that in a plasma. It's the stuff of stars. And then we create that graphene. We use that in a certain way. And then that's in that battery for X years or however many cycles it needs to do. And then at some point it needs to be recycled. You pull the aluminium off and you pull the graphene off. The graphene can be used again, and the aluminium can then be recycled, and it's 90% recycled already in the world. So that's also the other end of this, is that you've got this recyclable chain where, you know, you could really look at seeing how to reuse the same equipment in a very similar battery, or hopefully, you know, with a new electrolyte, when it comes back, we could put a new electrolyte in, which makes it even better, which makes it even more energy dense and perform even better. So that's even the potential there. So that's another space around how this could really change the way batteries are made, because lithium-ion batteries, people out there doing that, but it's not easy to do. And as we keep building bigger factories and making more of these lithium-ion batteries, which what we need to do, easily 10 times what we are now to be 2030, it's probably not even enough by then. So once you've had that, so where are these lithium-ion batteries going to go? You know, 600 to 1,000 cycles, you pretty much need to be pulled out and started again. And so that's, you know, that's that space. We need to be very, you know, focused on that. And you know, I think our battery can come in and help there.
Very nice. So a price very comparable once it's ramped up. Just one side question on that, and then I want to move to energy density. You talked about less machines needed for the manufacturing process. Is it, I understand that sometimes when you're manufacturing supercapacitors, and this is somewhat related, you can use dry process electrode manufacturing. Is it a dry process electrode manufacturing, or is it standard wet?
We can do both.
Okay.
We can do both. We're just exploring both. You know, which is really exciting, right? To have a dry process, you know, it's just effectively graphene and water.
Yeah, simple.
Yeah, that's really exciting, and our scientists are working on that. So where opportunities there are immense, John. I have to say because we're looking at anything that lithium-ion batteries have tried. We're looking at seeing how that could be used, and at scale. And that's what's really exciting is we're ramping through those different technologies and then looking at how that could be applied, and it becomes very opportunistic, very easy, because we're taking something that's already been scaled very successfully for the last 40 years. So that's also a really very unique way of kind of delivering a new technology when you can use the technology platform of another technology to get there.
The 9 machines you mentioned, that's wet process standard, the 9 machine
Yeah,
number?
that's wet. I mean, in a dry kind of process, you obviously have less. Yeah.
Yeah. Just kind of clarifying there. Okay, moving to energy density. So you mentioned the cell level energy density somewhere around 150 watt hours per kilogram. I think I saw on a presentation 150 to 160 in one of your presentations in the past. Now, as I talk about a lot on my channel, it's obviously that's an important number, knowing the cell level. But let's move to EVs for a minute. So obviously, I don't know if you've built any prototype, anything even close to this, but you can kind of maybe have an idea of what would be involved. From what I understand, from what you've been talking about and what I know from past conversations, you mentioned you don't need complicated BMS systems, most likely. Since it's a aluminum-based battery, it seems like it would heat and cool just instantly, almost like super quick. So you probably wouldn't need a complicated cooling system. So as an example, you take a Tesla's 2170 battery, lithium-ion battery, somewhere around 260 watt hours per kilogram, just the cell. You put that in a battery, and according to documents from the EPA, the Model Y has a energy density at the pack level somewhere around 180, somewhere around that watt hours per kilogram. So if you start with a aluminum ion battery with 150 watt hours per kilogram, I know you said you're going to improve in the future, but let's just say worst case scenario, it doesn't improve, which it will, but it doesn't. How much extra weight and stuff? What are we looking at? What kind of penalty when you add that to a pack? Are you much better talk about the cooling requirements, I guess, and what's needed in a battery pack?
So I mean, maybe I'll just sidetrack a bit and I'll come back. So the other product we have is a graphene energy saving coating, which can extract heat. And we're working on another project where we're an affiliate with Stanford University around how our graphene can transfer heat so fast, because it does an amazing job. And right now the theory we're working on is there's a few, but one of the main ones is it takes the heat and rotates it into a rotating phonon inside the atom structure, and then is able to take that heat basically into another medium. So that's what we're selling product on, for air conditioners, and that's what it does. It actually coats an air conditioner, and it can take the heat out faster and save you energy in your air conditioning. So imagine that then in a battery where heating is a big problem. The heat can actually be dissipated by our graphene. And I've seen that myself, we've seen that with our graphene, how we make it and how it gets used. So first of all, the product that's 50% of this battery is actually a heat absorbing and then somehow transferring that heat out, probably phonons. And then the second is the electrolyte is very sufferable to high heat. I think very, very quick, very anecdotally, we've done over 100 degrees and it doesn't seem to be an issue there. And then, so what are you left with in terms of its ability to overheat? Well, actually, probably not much. In fact, probably nothing else. Of course, we need to get to scale, but expectations are we'll be able to have a rack of these all sit next to each other, no cooling required, no air required, completely, you're talking 95% cell to pack density. And I think the earlier versions of the Tesla, I don't know the latest, but the earlier is about 50% cell to pack density. And then you don't have the 100 kilograms of cooling equipment, the glycol coolants. So that's a significant saving. And so I think what it does is it puts us at or around where lithium-ion batteries are at a scale battery pack. So when we talk to battery buyers and engineers in vehicle companies, we talk about battery pack density. It's exactly what you say. And we think we're quite competitive even where we are now. We won't have an energy drain of say 5 to 10% powering all of the cooling equipment. So there's another return to the battery density. And then we should be able to take any regenerative braking power back into the braking of, around corners and such things. We should be able to take all of that back, because right now it's limited. It's a lot of power, and they limit it to not blow up your lithium battery, not overcharge it, quite simply. So a lot of these high performance vehicles really want to see a high density push back, after a regenerative braking, and we should be able to take that as well. So it's a very interesting situation. The whole vehicle industry has definitely scaled off the lithium-ion chemistry, which is what it's had to do. But there are other chemistries coming through, and that will really challenge people on how you could actually run these EVs. For instance, the reason why the batteries are put under the floor and everything had to be redesigned was because of lithium-ion chemistry, because you had to cool it. But if you don't need to cool it, well, you could put these anywhere. You could split them up. You could put them per wheel. You could do, however the vehicle manufacturer wants to put them. So that's another point, is that it could well have some really interesting, challenging dilemmas for these vehicle manufacturers, they're all looking at the latest next tech. They all don't want to miss out on the next tech. They're all very, very concerned that in some way they might get left behind, or their product gets left behind because they don't get into this next battery tech. Because they all largely know that the lithium is what we have, but we need to move to the next one shortly.
It's a really game-changing technology when you understand it. And based on, I was looking at a presentation, and you show that as a comparison, a lot of the competitors that are working on, like maybe at universities and et cetera, that are working on aluminum ion batteries, they have energy densities like less than 70 watt hours per kilogram. And I guess you just kind of you have a very unique process that we talked about, drilling the holes in the graphene, and that process that really makes the aluminum ion battery, which wasn't really practical for EVs in the past, but it seems like it's going to be in the somewhat near future. Pretty incredible. That being said, let's move over to fast charging. You'd mentioned earlier, and also in a presentation I've seen that you guys put out, you talked about charging a phone battery in like 1 to 5 minutes. Obviously, that's a very small battery, but with the properties and the thermal benefits that you've mentioned, these battery cells, let's go to an EV scale battery. Let's say that the charging speed of the charger itself, the kilowatts being put out by the charger, that's not the limiting factor. So you have as many as you want, and does that battery charge in 5 minutes? And then as a second part of that question, so does the EV battery charge in 5 minutes if you can supply enough kilowatts to it? But second of all, you mentioned life. Does that really long life, if you fast charged it every time as fast as you could, would it last just as long?
So yes and yes. So we're sitting at 7,000 watts per kilogram with a pretty good energy density at that. So most people don't realize that, you fast charge a lithium-ion battery, eventually it will, and you keep doing that, it will deteriorate much faster. It's like you fast charge your phone, it will, every time, it will definitely get lower life. It will also have less energy, although it'll say 100%. As you know, it's not 100%. It's 100% of a lower number. So I think there's some interesting dilemmas for customers, for consumers, because it's quite a complicated thing. I liken battery charging to pouring water into a wine bottle, and you can really fast charge your battery. And you can pour a lot of water fast into a wine bottle, but then it goes everywhere, and you only get, say, 25% of it, say a quarter of it. And you think because you poured all the water in, but it's actually on the outside. And that's kind of like fast charging. You may not get 25, you might get 50 or 75%, but you're just pouring it in fast. So if you trickle the water into the wine bottle, then you actually get it full, and all that water goes in, and you're actually saying, I got this amount into that. And that's kind of what happens with the lithium-ion battery. Now, that's true of all batteries. Ours is less, there's definitely a lower energy density when you fast charge it, we come off about 10 to 20%, but we're still talking very, very fast charging. We're talking 70 times faster than what the lithium batteries are charged at. But fundamentally, and this is the issue with with our battery, is that it at scale, the grid will be absolutely not able to charge it as fast as it needs to be, or it wants to be. So it'll get charged at the rate that the grid provides. And so, you know, if you were to say, I want to charge your car, and sure, you could charge that whole battery in 5 minutes, but what it means is you have this massive thick copper cable, and then that would have to be connected to your car. So really the only way through this is that where you want to fast charge, you should have, say, a battery like ours or another battery that sits there and trickle charges from the grid, and then it can slam fast charge your car. But as it stands now, the biggest issue in fast charging a car is, you know, with this kind of battery, is the grid. That's definitely the case.
Moving to manufacturing. So obviously right now, I'll have you in a minute talk about your pilot production line and testing facilities and what that looks like. But when it comes to manufacturing these battery cells, it sounds like from what you've said, it's pretty easy to take existing equipment, adapt it to make these battery cells. It doesn't seem like there's a lot of changes. What does mass manufacturing look like on the assembling the cells, and also the process of putting the holes in the graphene, that process? Is that really very scalable? What does that look like at a massive scale?
Yeah, so I mean, maybe a bit around our team. So our team, including myself, is ex liquefied natural gas and upstream oil and gas and downstream kind of marketing in energy. So, you know, how liquefied natural gas, which is multi-$100 billion industry and has an amazing record around safety and delivery around the world for decades, literally keeps the lights on in various different cities. And without LNG ships, you know, docking, you set your watch by them, then, you know, there are people around the world who just wouldn't have energy. That obviously have some other type of energy, but they wouldn't have that clean energy. So that is all actually based, this massive, some of these projects are $30–40 billion. It's all based around a tiny little pipe as thin as your finger, your little finger, where the gas goes through and gets cooled and liquefied to negative 161 degrees. So that's been my background. So your gas comes in, gets liquefied, gets put in a tank, gets put in a big ship. That ship sails 8,000 kilometers, loses about 3% of the energy through the shipping process because it's boiling off at negative 161 degrees, and then docks, goes into a tank, and then expands, and then fills people's gas pipes and heating and such things and energy. So can our graphene process be expanded? Absolutely. If you can expand that tiny little chilling pipe into one of the largest industries over the last 60 years, you can do anything of different, you know, of small size. So our plasma systems are designed with that in mind. We've got Wood already working with us. They're one of the largest engineering crews in the world, and they just focus on now very much focus on sustainable kind of energy transition type projects like ours. And now they're very keen to kind of help out, and so we're getting them involved. That gas type project, what's great about these gas projects, and you know, and I know people might be saying, well, how do you get it from natural gas? Everything comes from under the ground or in the sea. There's nowhere else you can get stuff from. You know, I think eventually we would love to be able to take carbon dioxide and split the carbon and oxygen. We'd love to, but that's our end goal. But right now we're just focusing on methane and getting the carbon out of the hydrogen, making carbon. And it's the most abundantly available gas in the world by far, and the lowest cost as well. So, so yes, we can scale it. Yes, there's precedence. Yes, we've got the right team. Yes, we kind of, we think we can do it, and the capital efficiency is good and the cost efficiency is good. So then, what you're then talking about is, can we scale our Aluminium Ion batteries? And that's really around saying, well, what partners are you going to surround yourself with who've kind of done that before, who can do really good automation, and who think in that scale, that gigaplant scale. And that's why we went with Bosch, and also, we're working with Rio Tinto on the supply of the aluminium, and also for the purpose of using our batteries in their facilities and mobile equipment. So, that they're big partners to work with. We're excited to work with them, and I think they're excited to work with us. So then what we're talking about is making the graphene, splitting the hydrogen off, using the hydrogen probably to power our equipment, which is we do now, or maybe selling that. That's called turquoise hydrogen, not green, not blue. It's turquoise. For your viewers, it's got a category because it's from methane, but it's carbon sequestered hydrogen. It's not green. So then the carbon gets mixed into a slurry of some type, gets mixed into a cathode, aluminium foil, and then into a battery, and then we charge it and give it to people in appropriate pack sizes or formats. So we do think that this is very scalable, and we've been working with a number of different battery technologies, all different types of lithium, sodium, potassium, and we still do. We still supply our graphene out to different universities and companies, and this we got in front of this technology because of that ability to scale, because that's kind of where we come from, and we want to get back there.
Is the limiting factor the actual, you talk about drilling holes in the graphene? Is that actual just like a description of actually what happens, or is it when you put it together, it just naturally forms the holes? Is that a limiting factor at all?
No, actually, it's the simplest part of the whole process, which I believe, and that's actually already worked out. And it's actually a chemical process that we take the graphene through, but it's also you got to have the right graphene. And then there's a chemical process that you basically etch holes in the graphene, atomic holes, for the aluminium atoms to permeate or come into the graphene. That's not the issue. The biggest issue is making sure the right graphene is made every time, so that we know every battery, because every battery gets tested before it gets sent out in the world, or it should anyway, but it gets charged and then sent out. And so you've got to do that feedback loop. And because we have it all in one shed, we make the graphene, then we make the battery. We have this ability to test the battery with the graphene input. And that's really quite key. You couldn't do this battery if you were trying to do it separate, because graphene it's a quantum level product. It's subatomic level reaction. So you try to observe something and it does something else, and we've been doing it for many years, so we get how graphene behaves, and it's not always what you expect. So you've got to manage all of that. We call them learning loops, and you've got to manage these learning loops all within very tight tolerances, so you know what you're doing here to get what you're doing out there. And without that, you could not bring this battery to market. You just couldn't. But because our engineers and scientists are working and pulling this together, we can see, actually, this graphene makes this type of battery, that graphene makes this type of battery. So we can blend them, make composites, change the battery format depending on the graphene we put. And so we're seeing those things, and you just couldn't do it if you didn't have all that in-house.
That makes a lot more sense. I figured it was probably more of like a chemical process or something that made that happen. Yes. So good to know on that. I'd like to close our conversation. You've been given a lot of great information, but I'd like to close our conversation talking about your plans to commercialize the product once you are happy with what you have to commercialize this product. So talk about the plans there, and then within that, talk about your progress with your pilot production line, your testing facility, and where that goes in the future.
Yeah, so first of all, we're trying to get something out to show the world, including ourselves, that we can make batteries in an automated sense. And so we're picking coin cells because, honestly, coin cells are the first thing that needs to be disrupted in batteries. Their lithium batteries are needing a next gen in coin cells. There's little watch batteries. In Australia alone, there's 60 kids die a year from eating a coin cell. And they don't get it because the packaging is not correct. They get it because they're hanging around a house and and the kid picks them up, after being used, and they're in the people in the drawer, and we've got to, that's an opportunity where we can make a direct impact and start producing millions of those. And look, if everything comes together, I mean everything has to come together. We try to pull this out and push this into a production plant sometime next year, and maybe we might see it back at end of next year. That's what we're really trying to do. And if we can do that, then we've shown how to bring the chemistry and the graphene and the production and the automation and the marketing all together. And then in the meantime, we've got hundreds of companies wanting our pouch cell, and some of them, the biggest in the world. So how to play with that, John? It's like drinking from 4 water hydrants. It's all at the same time. It's you're just constantly trying to get through what's coming at you, and trying to work with people who really want to collaborate and want to work with you, but also want it all yesterday. They just want this tech out. And so what we try to do, like Rio Tinto, we try to work with really collaborative type companies who can see the ability to add value to us. So we hope to come out, at some point and say, well, here's other companies like Rio who want to work with us in a collaborative style with our battery on how our battery could help them. And that's, the kind of the space there. And then once we've worked out exactly what type of form factor, most probably a pouch, what size, the energy density, what's the situation, your use case, then we'll start thinking about locating that first plant. So that's another thing, the next stage. So once we've shown that we can do the coin cells, then we do some kind of pouch cell factory. Then we say, well, right, where do we want to put these battery factories?
Well, very wonderful, Craig. If you just want to leave us with any closing comments that you have, I will put a link to your guys' website in the video description for those who are curious to learn more about the Graphene Manufacturing Group. But if you just want to leave us with anything that you want to close my audience with.
Yeah, I think it's what I want to say is, I guess, thanks everyone for their support. This is a hard task, bringing a new type of battery chemistry at a kind of nanomaterial level out to market, and we do have an amazing amount of support. So keep it coming. We need that. We've got to bring this. We've got to add to what lithium battery is doing, and other batteries are out there, and obviously hydrogen as well for the energy transition, and all the other various ways we're making renewable energy. And so please keep it coming, guys, because it's important. We all need to put shoulder to the wheel to make this happen. This energy transition is not easy, and there's a lot of work to be done. So very cool. Thanks for the support.
Sure. I'm definitely pumped about you guys, your technology and your company. And thanks for taking time to talk with me.
Thank you, John.
Well, thank you so much for watching this video all the way through to the end. I'd like to take a moment to thank the Patreon supporters who support me every month and help make this content possible. A special thank you to my performance supporters and also the other supporters listed on the screen. If you'd like to find out more about the Patreon community I've set up, I'll put a link in the video description. Thank you so much.